In OpenStax Calculus Volume 2, we're in Section 3.4 on partial fractions for integration, and we're going to look now at the problem-solving strategies that the book provides. So, to use partial fraction decomposition, my top degree needs to be lower than my bottom degree. If not, we use long division. After that, you factor your q of x, which is the bottom. So far, we've had all linear factors, but we're getting ready to talk about some quadratics. An irreducible quadratic factor, that's a vocabulary word we need, is a quadratic that has no real zeros. Assuming that your degree is less on top than the bottom, that the factors are, then the factors of q of x, the denominator, determine the form of the composition. We've already done this. If the factors on the bottom are linear, then the top is constant. Repeated linear factors have to be repeated as many times as that power says. And if I have a quadratic on the bottom, then the top has to be linear. If we had a cubic on the bottom, then our top would have to be quadratic. We don't do that very often. So let's go ahead and work with some quadratic factors to start off with. Here, if I broke this up, my denominator is x times x squared plus 1. If I tried to factor x squared plus 1, or if I tried to solve it, I would get imaginary numbers, so no real roots. So I have a linear and a quadratic. So we have 2x minus 3 is our original. We're going to do x on the bottom, and we're going to do x squared plus 1 on the bottom. So this one's going to get a constant, and this one is going to get a linear factor. All right, to get my common denominator, I'm going to do x squared plus 1 here, and x here. I have ax squared plus a plus bx squared plus cx over x squared plus 1. Now we're going to do our like terms. So we're going to start with the x squares, which I don't have any in my original denominator or numerator. So I have a plus b equals 0. Then my x's, cx equals 2x, so c equals 2. They made that easy, didn't they? And then a is my last one, my constant, equals negative 3. So a equals negative 3. Negative 3 plus b equals 0, so b equals positive 3. And then we use that template that we made here to rewrite. Integral a, which is negative 3, over x, plus bx plus c, so 3x plus 2, over x squared plus 1 dx. This fraction right here still doesn't quite work out, so what we're going to do is we're going to break it up and use this denominator for both, which is acceptable. I could have done 2x over x to the third plus x, and then negative 3 over x to the third plus x, but that didn't do us any good. So here I have integral of, I'm going to bring my negative 3 out and put this as dx over x, plus, if I use the 3x, I'm going to do 3x over x squared plus 1 dx, plus, I'm going to bring the 2 out, and I'm going to put 1 over x squared plus 1 dx, which actually I needed that too, and that's okay. We'll go back and fix it. Here, if u is x, then du is dx, and this is negative 3 ln x, plus, if u is x squared plus 1, du is 2x dx, 2 there, 1/2 there. So we have 3 over 2 ln x squared plus 1. Plus, on this one, the 1 over x squared plus 1. So we're going to go over to the side again because this one is a little bit different. I want to make sure you know how to use the rule for it. We have 2 integral 1 over, I'm going to rewrite it as 1 plus x squared dx. Well, if we look at our rules, the one that fits this the best is our arctan or inverse tan rule. And that says that my a is 1 and my u is x because they want a squared plus u squared. du is dx, which fits right here. So 2 times 1 over a inverse tan u over a plus c. So it'd be 2 times 1 over 1, we're good, tan negative 1 x over 1 plus c. So if I go back right here, 2 inverse tan x plus c. Now, technically, I could take the absolute values off here because x squared plus 1 has to be positive, but it's not a big deal if you have it or if you don't. All right, looking at the next one. X to the third minus 8 is a difference of perfect cubes. I don't know how many of you learned the SOAP way of factoring these. X to the third minus 8. So, like I said, the SOAP method is what I use usually to teach this, and that's that this is x to the third minus 2 to the third. So you would have x and 2, x squared, 2 times x, and 2 squared. And SOAP means that you have the same sign as the problem, the opposite sign, and always positive. So this is my denominator, and my numerator is 1, because my dx is just sitting there. Okay, so if I break this up into x minus 2, that's linear, so it gets a constant. And x squared plus 2x plus 4 is quadratic. It does not break down. So that's got a bx plus c on top. I'm going to multiply by x squared plus 2x plus 4 here. And by x minus 2 here. All right. Algebra for the win. X minus 2, x squared plus 2x plus 4. Distribute my a. 2ax plus 4a. Foil or box the bx plus c and the x minus 2. So we have bx squared minus 2bx plus cx minus 2c. All right, all of that needs to equal 1. So when we do our like terms, my x squares are here. I'm going to go ahead and highlight everything first. My x's are here. And my constants are here. So starting off with my x squares, my original problem didn't have any. So I have a plus b equals 0. For my x's, I have 2a minus 2b plus c equals 0. And for my constants, I have 4a minus 2c equals 1. When I start over here, I change this to a equals negative b. So this would be negative 2b minus 2b plus c equals 0. Negative 4b plus c equals 0. C equals negative or positive 4b. So when I go to this last one, for a I put negative b, so negative 4b minus 2 times 4b equals 1. Negative 4b minus 8b is negative 12b equals 1. So b is negative 1/12. That means that c, 4 times negative 1/12, is negative 1/3. And a is negative 1/12, which is positive 1/12. So now let's go back and use our pattern that we made to rewrite the problem. So a, which was 1/12 over x minus 2, plus bx plus c. Well, b was negative 1/12 minus 1/3 all over x squared plus 2x plus 4 dx. Let's rewrite this a little different. I'm going to bring out my 1/12, and I'm going to make this one dx over x minus 2. This is going to end up being minus because I'm going to take that out there. So what I take out is a 1/12, and that gives me x plus 4 over x squared plus 2x plus 4 dx. When I look at this one, the first part is pretty easy. U equals x minus 2, so du would be dx. And that's the typical Ln rule, so 1/12 Ln absolute value x minus 2 minus. This next one, I'm going to keep my 1/12 there, and then we're going to wait. Because this guy, they really gave us a challenge here. So let's go over here. Integral x plus 4 over x squared plus 2x plus 4 dx. This does not fit our rules. If u was x squared plus 2x plus 4, then du would be 2x plus 2. And I can't make x plus 4 into 2x plus 2 without, I don't know, some magic. So what we do, because a lot of our rules have an x squared and an a squared in the bottom, is we're going to complete the square. And it's probably been a while. I'm showing you all kinds of algebra in this lesson. You mark off your ax squared and your bx. There's no GCF there in a number. You don't take the x out. So I'm going to rewrite as x squared plus 2x plus blank plus 4 minus blank. Then you take this middle term divided by 2 and you square it. And that goes here and here. So now we have x plus 1 squared, which was the whole purpose of doing this, plus 3. So I'm going to rewrite my problem as x plus 4 over x plus 1 squared plus 3 dx. All well and good. Still doesn't match any of my rules. So now if I say u equals x plus 1, du equals dx. So, this is so weird. I want this to say u squared plus 3 du. But how do I work out this top piece? Well, right here, u is x plus 1, so u minus 1 is x. So if I put a u minus 1 right here, then this top would be u plus 3. Still weird, yes. However, now I can break this up into u over u squared plus 3 du plus 3 over u squared plus 3 du. Here we have, if my u, I'm going to make v, is u squared plus 3, then my dv is 2u du, so I need a 2 and a 1/2, and I have 1/2 ln u squared plus 3. Put your x plus 1 back in there, 1/2 ln x squared, nope, x plus 1 squared, sorry, plus 3, which if I do my work back out, it's x squared plus 2x plus 4 because that's what we had. I still have another piece, but let's go put this back in our answer. Sorry, can't get to it. There it is. So right here we have 1/2 ln x squared plus 2x plus 4 plus whatever we get for this next part. So on this next part, remember the rule that we did for inverse tan earlier? So inverse tan, I got to look, is the integral of du over a squared plus u squared equals 1 over a inverse tan u over a plus c. So I'm going to turn this around to be integral of, I'm going to put the 3 out here, du over 3 plus u squared. So a is 3, u is u, which is x plus 1. Double checking everything. So let's write that as x plus 1. All right. So a is the square root of 3. Sorry. I have 3 times 1 over the square root of 3 inverse tan u, which is x plus 1, over a, which is the square root of 3, plus c. So when I write that into my final answer, I have 3 over the square root of 3, inverse tan x plus 1 over square root 3 plus c. So let's write our answer a little more pleasing than that. So our answer ends up as 1 over 12 ln of x minus 2 minus 1 over 24 ln of x squared plus 2x plus 4 minus, when you do all your rationalizing, square root of 3 over 12 inverse tan of x plus 1 over square root 3 plus c. Final answer. But this one's going to take a little bit to load.